Professor Weiss, congratulations on winning the 2024 Basic Science Lifetime Award. We are excited and honored to have you here in Beijing. Have you been to China before?
I've been once before to Beijing and to Hong Kong. Yeah.
So how has your trip been so far?
Oh, it's been wonderful. Wonderful hospitality. We love the environment. It's been very, very nice.
So how does this trip compare to your previous experience here?
It was a long time ago and I've forgotten, but it seems it's very peaceful where we are. China has become very successful and energetic. It's very exciting.
This is the second year of the ICBS. The goal of this annual congress is to bring together leading researchers in mathematics, theoretical physics, and also theoretical computer and information sciences to discuss their current work. It's quite impressive to see so many distinguished researchers in one place. What do you think are the virtues of organizing such a conference?
Oh, I think it's wonderful to bring together people from many countries and many disciplines. That is always how mathematics and science in general have prospered, when we talk to people in other countries with other knowledge of mathematics. We share our ideas. One person can solve one thing, another person solves another, and then they put the ideas together and they can solve something new.
So you received the award for your groundbreaking proof of the Taniyama-Wei-Shimura conjecture, which led to a solution to Fermat's theorem, had transformative impact on number theory. While many people know you solved the Fermat's theorem, fewer people understand the Taniyama-Wei-Shimura conjecture. Could you explain this conjecture and your work to non-experts?
Well, it's difficult, but I can try and give an idea of what the issue is. So Fermat's last theorem, for example, is a problem about solving an equation. And this equation, the famous equation, x to the n plus y to the n equals z to the n. But there are many other equations that we want to solve. Perhaps the next equation that many, many people like to solve, and is the big challenge of today, is the problem of elliptic curves. That is an equation like y squared equals x cubed plus 3, or y squared equals x cubed plus 17, or y squared equals x cubed plus 3x plus 5. These are all elliptic curves, and we don't yet know how to solve these equations. We have an idea how to solve them, and by solve them I mean in rational numbers, that's in fractions. We have an idea how to solve them, and we hope to prove that one day as mathematicians. The Taniyama-Shimura-Wei conjecture was the first step towards this, because it said that there should be a way using a very special function that will solve this equation, the L function of the elliptic curve. But until that equation, that conjecture was proved, we didn't understand this L function. And now we understand it much better.
Thank you.
So when I was a high school student deciding to study mathematics, I was deeply inspired by the 1996 BBC documentary about your work on Fermat's last theorem. I must have watched it more than 10 times back then, and it played a major role in my decision to pursue mathematics. It's really a privilege for me to speak with you in person today. So could you comment on the impact of your Fermat story on young students?
Well, I think you've made the comment. Many people tell me this, and even non-mathematicians get very excited by the story, because in some sense, all these mathematics problems are stories. For people who are not mathematicians, telling them as stories makes it much easier for them to understand. It makes it easier to understand the excitement of mathematics when they hear the story. Otherwise, they might think it's just a difficult problem in a classroom and they want to go out and play football. But if they see the story, they can see why it's so exciting, why people will spend years trying to solve the problems like this. So I think they did a very good job with the program, making it appeal to non-mathematicians. So one of the people who made the program was not a mathematician, and he was caught by the story, and I think he tried to convey that.
In the documentary, you mentioned that Fermat's last theorem had been a childhood dream since you were 10 years old. And when you later started your academic career, as you mentioned, elliptic curves was your research area. So what made elliptic curves your research area at that point?
I think it was very much because my supervisor at the time was John Coates, and he wanted to work on elliptic curves, and he suggested we look at this problem together. It's a problem called the Birch-Swinnerton-Dyer conjecture, which tries to tell you how to solve these equations using what I described, this L function associated to the elliptic curve. So we made some exciting progress on this. We found one way of showing that there were no solutions. But the real challenge is to find the solutions when there are solutions.
So the BSD conjecture is one of the deepest open conjectures in number theory. Could you describe the situation back then when you worked on this conjecture in Cambridge?
Yes, so at that time, the conjecture had not been families of examples where the conjecture was known. So you could check it, at least in the approximate form, you could check it for an individual curve. But there were no general results at all. And no one had an idea how to approach the problem. But there was one class of curves for which the Taniyama-Shimura-Wei conjecture was already known, had been proved by Shimura. And that was a special group of elliptic curves called ones with complex multiplication. For example, the ones like y squared equals x cubed plus 5, y squared is x cubed plus 71, the ones I was talking about before. These have complex multiplication, and we found a way to study these. We were able to show that you could compute a number, and if this number was non-zero, then there were very few solutions for the equation. You could find them all. Number that we showed how to compute was one particular value of this L function. And there's a formula for it. So it gave a kind of formula you could test. If you look at this formula, you look at the value. If it's not zero, then you can find the solutions. If it is zero, then you have a different problem. Then we conjecture, but we don't know that there are infinitely many solutions, and we don't know how to find them.
Okay, so then let's come back to the Taniyama-Wei-Shimura conjecture. So when you decided to tackle this conjecture in the 1980s, was the consensus among other mathematicians that this conjecture was out of reach? And so how did you have the insight that this was actually something that could be solved?
I think the consensus probably was that it was out of reach. Otherwise, presumably more people would have worked on it. I didn't have the idea it could be solved. I just found it irresistible. Once it was linked to Fermat's last theorem, I stopped thinking about Fermat's last theorem after childhood because too many people had wasted too many years on the problem, and professional mathematicians did not think it was a good idea to work on it. They would tell you not to work on it. But after 1985, it was known that there could be a link. So in 1985, Gerhard Frey suggested a way that you could approach Fermat's last theorem if the Taniyama-Shimura-Weil conjecture were true. His idea wasn't quite right, but after work of Serre and then a theorem of Ribbit, we found out that yes, if you could solve the Taniyama-Shimura-Weil conjecture, then you could prove Fermat's last theorem. And the day I heard that had been solved, I immediately started to think about it. And did I think I could do it? I didn't worry about that. I just thought about it.
I see. So when you started, you didn't even have a clue where to start, or
no?
Yeah. So maybe in hindsight, it was a really long project. So
yes, I knew it would be a long project.
Right.
But
so how did you in some sense make the first meaningful step in this long project?
I think I took some inspiration from a paper of Barry Mazur, and what I tried to do was to understand what might happen if you had an elliptic curve with a special property that it had a point or a subgroup, small order, which was rational. So, for example, if it had a point of order 5, which was rational, or the subgroup was rational. And in those circumstances, Barry Mazur had understood a great deal about what is called the Hecker ring. And I tried to see if I could deduce anything about the elliptic curve from knowing this. And I just spent a long time thinking about that. It's interesting when you have a long project like this, a problem, and you don't know what the entry point is or how you try it. Sort of half the time, it took 8 years, but half the time, you're just looking for the right area. For a year or two, you get nothing. You're trying bad directions, and you have to rule out the hopeless directions and find something that seems to have a link. And maybe every 2 years, I first, after a year or two, I got some idea. I could try it via the Galois representations. And then after 2 more years, I understand I've got to look at how all the different Galois representations fit together and so on. So the early part is it feels like you're not really achieving very much. And then, of course, near the end, you achieve a lot quite quickly.
Yes. So even studying, so the idea of studying deformation theory of Galois representations was not clear at the beginning, or?
No, in fact, I didn't realize what I was doing was deformations. I didn't know about deformation theory. I was doing it without realizing that was what it was.
I see.
But that doesn't matter. I mean, you just recreate some of it. No, I think it was Barry Mazur who realized later that deformations, the Galois representations had good deformation theory, and it was interesting to study.
The TWS conjecture is a part of Langland's program.
Yeah.
So which aims to unify various areas of mathematics. Currently, do you see something in the Langland's program that is both challenging and within reach, similar to the Taniyama-Weil-Shimura conjecture in your time?
Yes, I do actually. I've thought for many years about the Langland's program, and I think I will explain in my talk what I think the approach for a number theorist should be. Roughly, I think the idea of the Langland's program for a number theorist is to understand non-abelian extensions. And abelian extensions were class field theory. But when people think about the Langland's program, they tend to forget about class field theory or treat it as something from long ago. But I think actually the methodology is very useful in thinking about non-abelian representations. I think there's a similar methodology, and I will try to explain how I think one should try it.
Okay, so the next question may also be a preview of your talk. So I saw that you recently gave a talk with the title "A New Approach to Modularity." Is this your current research project, and could you tell us more about it?
Yes, I will talk about a little about it in my talk. So I've been trying to understand how you could prove that elliptic curves are modular, in particular without using special tricks for p equals 3, which was used in the original proof. One wants an argument that's much more general for starting. I think the arguments are closer to class field theory. I think one of the problems has been that class field theory developed over many years, and the proofs changed steadily. So no one's quite sure in the proofs of class field theory what makes it work. They can be very confusing. I mean, at a local level, they are not too difficult, but to try and see why are you doing this is not so obvious. I think, like all things in number theory, at least many of the best results in number theory, the technique seems to be to make some kind of explicit construction and to use analysis to show that you have everything. I worked for some years, first with Maser and then on my own on the Iwasawa conjecture, and that was certainly how that worked. And in some sense, that should have been how the modularity proof worked, the FMAR worked. You make an explicit construction. You have Gauer representations coming from modular forms, and you need to know that's everything. And you should have used an analytic statement to prove that that's everything. And I think finally now people may be able to do that. But at the time, the analytic proof was out of reach and it didn't work. But luckily, there was an algebraic method instead. And I was very fortunate because I thought it ought to be analytic at the time. And then I realized that there was a very nice algebraic way of doing it. But for number theory in general, I think analysis is very often the answer. And when I say analysis, I'm using L functions, special values of L functions via class number formulae or something like that.
Do you mean to use analytic methods to show you get everything? Do you mean some kind of counting or?
It's counting. So you construct things and then you have to know they're enough. So you use the L functions to give a bound on the count some way.
I see. So actually, this also reminds me of, and you also mentioned there were various different approaches to class field theory in history. So at first, people just had global class field theory, and analysis definitely played a major role in the proof.
Yes.
And later, people came up with a purely local proof of the local class field theory, and then used algebraic methods to get the global class field theory. So for the Langlands correspondence, I think currently the local Langlands conjecture for the general linear group is only proved using global methods.
Yes.
But maybe we're closer to a purely local proof, but still not quite there. So do you have some insight on this situation?
No, I don't have any. My feeling is that class field theory, it's more helpful to think about the old version where you use the analytic method. I'd be surprised if we can do the Langlands program without the analytic input. The problem is, and I think Langlands tried this, you can very easily think of very, very useful analytic things to prove, but most of them are hopelessly, difficult analytically. So the challenge is to find an analytic statement that you can actually hope to prove.
So is your circle of ideas also related to Langland's idea of beyond endoscopy in any way?
So that's what I'm saying. I think Langland's idea required too much of the analytic number theory, and I don't think the analytic number theorists can really help with it. So I hope that what I'm trying to do, but the analytic side, what I use from L functions is already fine. It's not hard.
Professor Weiss, in your career, you have worked on several really challenging and groundbreaking projects. All of us are impressed by the fact that you are always be able to find exciting and deep directions. Could you give young people some advice in this aspect?
I think perhaps when you're very young, you shouldn't start with these problems. Because if it takes you too long and it's your first problem, you will give up. So you need to start with some problems that can be done in a year or two. But then when you've developed some intuition, also you've learned how to deal with being baffled by a problem for a long time, then you can move on to these longer term problems. For me, and perhaps for many people, you really learn how to tackle at least these more accessible problems by being in a community. You learn it from your supervisor, you learn it from your peers, your colleagues, and so on. So very few people can start off doing it entirely on their own. Some can, a few very gifted people, but I didn't, and I was very lucky.
Thank you.
So currently, it seems to be the case that in our subject, even these 1 year or 2 year projects, the papers end up to be really long, like 100 or 200 pages, and it also takes a really long time for the paper to be refereed. So in some sense, I think this actually poses some challenge to young people who are still seeking for a permanent job. So do you have any thoughts on this situation?
Yes, it's unfortunate they're getting so long. I don't know what the explanation for that is. Maybe we're missing some shortcuts. I don't know. It's an interesting question.
So you have mentored many successful students at various places, such as Harvard, Princeton, and Oxford. So what is your approach of training PhD students, and are there differences among these different places?
So I think with the students, I like to find the problem together. I don't just decide this problem has to be for this student, because different students have different talents and also different tastes. And it's good to find a problem that captivates that student and responds to their skills. So for example, for me, perhaps one of the easiest was Manjul Bhargava, because he had incredible sort of combinatorial and discrete mathematics skills already, and there was a problem that I wanted to see solved, and so I just mentioned this problem, and then he got incredible results from it. It's not a problem I could work on myself. I wouldn't know how to do it. So that's the easiest kind. But sometimes the first problem doesn't work, and then I realize that maybe the problem is too hard, or maybe it's not quite the right problem for the student, and then I hope that we'll find together what the right problem is. Because you're right that in some sense, finding good problems to work on is one of the most important skills for a mathematician. And this is the place to learn it as a graduate student. It's not obvious to people which problems are the right problems to work on. Even to me, then it's not obvious. I don't know in advance. Sometimes I can see from my work that this is going to be a very important problem and no one's really worked on it much. So then, yes, I can just give it to a student. And that works very well. But often you don't have such problems available and you have to find it. And your second part was Oxford and Princeton, Harvard. Different places, they're very international. So the students at Harvard or Princeton, even at Oxford, will have come from other places like Harvard or Princeton or Oxford or anywhere in the world. So in some sense, the students aren't different, but maybe the communities are a little bit different when they get there. And some are much more unified in field and very collaborative. So Harvard, for example, maybe many students who are working with a small number of people in the same field. And then they learn a lot from each other and they can run seminars together and so on. Maybe somewhere else, you might find that the faculty have very different interests and the students have very different interests and they're going to be more on their own. And that has its own challenges. But the students themselves, they come from everywhere and they go everywhere. So it's very international.
I see. When I was a graduate student at Harvard, I found the atmosphere there among students to be really, really competitive. It seems that all the grad students, they wanted to prove that they were better than the other people and smarter than the other people. But later, when I did my postdoc at Columbia University, I found that the graduate students there, they actually had a very different atmosphere. They were much more collaborative and more friendly with each other in some sense. So which way do you think is actually better for early career mathematicians?
Well, I think that it's better if you are a very competitive person, you want to go to a competitive atmosphere. If you're not, it's better not to. I think, I don't know whether these feelings you have at Harvard, whether it would be the same 5 years later or not. I think some of these universities as undergraduates can be very competitive and some not at all. And it's partly how they're recruited. Some universities will recruit heavily from maths competitions. Some will recruit from completely different ways, and the people have no experience of competition. I think the important thing is to pick an environment that you like, that suits you. I mean, some mathematicians more interested in being on their own and just thinking by themselves for a long time, and some like to be in an atmosphere where everybody is talking and competing. And
Could you recommend a particularly good article or book that every mathematician or perhaps everyone should read?
One very short, simple book I really liked was A Mathematician's Apology by G.H. Hardy. It's an old book now, but some of the things he said no longer are true. For example, he said number theory has no uses. But he presents, I think, mathematics to non-mathematicians very well. Very short, simple book. For a mathematician, Sayre's A Course in Arithmetic is a wonderful short book that is filled with many, many ideas, beautifully expressed.
Okay, thank you very much.
Thank you very much.